In this video, I'll be explaining to you the magnetic field at a bisector on a current carrying wire. In this animation, you can see the direction of the current flowing around the wire in a pink arrow and the direction of the magnetic field. If you see a still image, we can see here that the current direction starts from the positive terminal of the battery, marked there as plus, and the current goes all the way around to the negative terminal of the battery, which is marked as minus. With this current direction, the direction of the magnetic field is automatically decided. You can see a right hand in this sketch, where if we apply the right hand thumb rule, the direction of the thumb indicates the direction of flow of current, and the direction of the fingers, which are curled around the red wire, indicate the direction of the magnetic field. Basically, the fingers are supposed to indicate concentric circles. The moment a current flows around a wire, the magnetic field gets set up in the form of concentric circles. There would be infinite circles, of course, starting from right to left. I have shown only two. And also, at any given point, there would not be just 3 circles. There would be a large number of, infinite number of circles. The magnetic field strength decreases as the circle becomes bigger and bigger. If you look at another view of the same sketch, you can see that the direction of the magnetic field is clockwise in this case, in the sense that on the right hand side of the wire, the direction of the magnetic field is tangential to that circle. That's all the green arrows are pointing downwards. And on the other side of the circle, the green arrows are again tangential to the circle and they are pointing upwards. So at any given point of time on that circle, you can find the direction of the magnetic field referring to the animation. We now take a quick revision of the equation for a point P, which is randomly placed, which is really not on a bisector of the wire Mn. So we plucked out the wire of length Mn from the earlier sketch, and you can see the same red wire here. And if point P has to be if the line OP has to be a bisector, it should actually divide Mn into 2 equal parts. But right now, we are revisiting the equation for a general point P. The point P is therefore on the right side of the wire. The current direction is most important. That's shown by the pink arrow. The magnitude of the current is I amperes. And because the current is flowing from end to end, the concentric circles are of course having a magnetic field direction which is clockwise. So at P, the magnetic field is pointing into the plane of the paper, and opposite to point P on the other side of the wire, the magnetic field direction is upwards from the plane of the paper, which is a dot. So now the equation is taken from an infinitesimal length dl, which is randomly put on the wire, and this dl subtends an angle theta to the point P. The dl itself is at a length L from the point O. The OP, by the way, is perpendicular to Mn. The point M, which is the lower edge of the wire, subtends an angle theta 1 with P, and the point N, which is the upper edge of the wire, subtends an angle theta 2 with P. The distance OP, the radial distance OP, is d, and the distance of P from the infinitesimal length dl is equal to a radial distance r. With this, the infinitesimal magnetic field dB is defined as mu0 by 4 pi into I into dl into sine theta by r squared. When we integrate this dV over the entire length of the wire, there's many dls, we will get the value of the magnetic field, that is B. This slide shows the definitions of the various things that we put into our earlier slide, and it gives an explanation of what is what. When we integrate dB over the entire length of the finite wire Mn, we will get the value of the magnetic field strength B at point P as μ0 by 4 pi into I divided by D into cos theta 1 minus cos theta 2. Here B, magnetic field strength, is defined in the unit Tesla. μ0 by 4 pi is a constant, it's 10 to the power minus 7. I is the current in amperes, and D is the distance between O and P, that's in meters. We now come to the bisector. Now the point P is placed such that the whole concentric circle is midway between M and N. Please go back to my animation and the sketch to imagine those concentric circles. So point P is on this concentric circle, and therefore OP is of course perpendicular to MN, but the line OP is placed such that OM is equal to ON. So you can see A on the left hand side marked out. So OM will be A by 2 and ON will also be A by 2. The remaining things are the same. There's no change in the direction of current, no change in the direction of the magnetic field, that P, and so on. We now have to simplify the equation. That's the previous equation that's valid for any point which is randomly located in the space around the wire. Now in that equation we cannot simplify the current I or the distance D or μ0 by 4 pi. We can only work on cos theta 1 and cos theta 2. So let's do that. Cos theta 1 is the angle OMP, and that's adjacent side by hypotenuse. The adjacent side is the length A by 2. The hypotenuse, use the Pythagoras theorem, that's A by 2 whole squared plus D squared, and when you simplify that you will get A by root of A squared plus 4D squared, as you can see. Similarly, for the obtuse angle theta 2, that cos theta 2 will be minus of A by root of A squared plus 4D squared. Let's now plug this into the main equation and see what happens. Now B is equal to μ0 by 4 pi into I by D cos theta 1 minus cos theta 2. That is the A by root of A squared plus 4D squared minus A by root of A squared plus 4D squared will become 2A by root of A squared plus 4D squared. So we get this equation simplified to B is equal to μ0 by 2 pi into I by D into A by root of A squared plus 4D squared, plus 2 cancels with 4. That's it, and we have got this simplified equation. I hope this was useful to you. If you have any queries, feel free to write back at the messages. Do subscribe to our YouTube channel, share it with all your friends. You can log in free to our websites depending on whether you're in India or abroad. Login is free. The course is paid. Have a great day and see you soon.